In this presentation, we are going to explain the layout and the function of a helium-neon laser system. It consists of a DC power supply for the pumping process necessary to get a population inversion within the amplifying medium. A glass envelope encloses an anode and a cathode, and an output coupler, and a planar mirror and a lasing medium. Anode and cathode are ring-shaped and placed on opposite sides of each other to be able to get an electrical discharge. The output coupler has a reflectance of 99% and allows the beam to be reflected for the laser amplification and enables the operator to use 1% of the light for the output beam. The planar mirror has a very high reflectance of 99.9% and is placed parallel to the output coupler. The lasing medium itself consists of a specific neon-helium gas mixture. To explain the pumping process necessary for the laser amplification, the band module comes handy. Helium, in its ground state, consists of a core composed of protons and neutrons and 2 electrons in the 1s state, as shown here. Here we see the electronic configuration of neon. The pumping process is induced with the anode and cathode, which are exposed to a high voltage, producing an electrical discharge within the amplifying medium, here indicated with a flash symbol. This causes the electrons to collide with the helium atoms present in the glass envelope. The collision energy of these electrons causes the helium atom to get to an excited state.
To consider an alternative representation of these processes, we can look at an energy level diagram for the helium-neon system. The collisional excitation of the helium atoms raises them to a state with energy of 20.61 electron volts. The coincidence in the energy of this state with the 2s and 3s levels in neon means there can be an efficient transfer of energy through elastic collisions between the two species in the lasing medium. Returning to the band structure of these substances, this energy exchange is made evident. Helium atoms return to their ground state, while neon atoms are excited to an energy of 20.66 electron volts. This metastable state is responsible for slow radiative decay. The decay typically takes 100 nanoseconds and causes the emission of a photon at 632.8 nanometers, shown here by the red line. By contrast, the subsequent decay is much faster, with a relaxation time of 10 nanoseconds. The order of magnitude difference in the relaxation times of the metastable state and this state is crucial for achieving a population inversion, whereby the number of atoms in the excited state far exceeds those in the lower energy states. The remaining energy is dissipated due to collisions of the constituent atoms with the walls of the glass envelope. This is made evident by the fact that the neon atoms have decayed to the ground state. A key feature of the helium-neon laser is its spectral purity. The lasing medium, being held at low temperature and pressure, ensures that Doppler broadening is the dominant source of line broadening, allowing the laser to produce a very narrow spectrum with a high gain at 633 nanometers. These characteristics make the laser suitable for disk reading, though it has been primarily employed in the academic sector for a number of tasks in the laboratory. The functioning of the helium-neon device is best illustrated using the energy level diagram for this system. Let's return to this slide for a recap. Firstly, helium atoms are excited from the ground state due to the electrical discharge across the glass tube. Collisions between the helium and neon atoms provides a mechanism for efficient energy transfer for the excitation of neon. A slow decay from this state results in the emission of a photon at 633 nanometers, which is then amplified in the laser cavity, while the remaining energy is dissipated away. Thank you for listening to our presentation. Please find the references used here.